Sugar last summer with two wonderful students. So they're going to share with you the project and what they did and then answer questions. And let me tell you, Sugar is the undergraduate research in the arts and science. 8 weeks they have to finish a project. These two had no experience writing code beforehand, and they built a whole simulation and did data analysis in R in 8 weeks. I'm really proud of them. So I'll let you have Caitlin and Jennifer to share with you our project.
Hi everyone, thank you all for being here. Jennifer and I are very excited to share our research with you. Like Dr. Browning said, we studied under him over the summer for the university's undergraduate research program, and in order to construct our binary lattice system, we had to learn how to code. So we had to learn a whole new coding language, and we had no background in it whatsoever before we started. But specifically, we had to learn how to code in NetLogo, which is a program that we use to organize the model. And before we explain the properties that we tested temperature, entropy, and energy. We're going to walk through the foundation of how we built this model and how it was organized. The binary computer-based model has two systems of spins, and the space where these systems interact was divided by color. So one system was blue, while the other one was pink. We referred to the blue group as spin group A and the pink group as spin group B. Now, additionally, both of these spin systems contain two different spin states. So the darker colored patches are the excited nuclei, and the lighter colored patches are the ground state nuclei. And these spins can be flipped by neighboring spins, so they can be flipped to either the excited nuclei or the ground nuclei. So the colored patches are the nuclei of the systems that we created to manipulate and change their abundance within the model to produce different outcomes based on the two systems' interaction with each other.
Okay, so how it works, as Caitlin mentioned, we have these patches that are representing nuclei, and they're constantly interacting with each other. So when they're interacting, they can flip to be excited if they're at the ground state. And so we have a nuclei that's surrounded by its neighbors. If majority of its neighbors are excited, that nuclei can flip to also be excited. So you have these nuclei that are constantly in interaction with each other, flipping to their energy states depending on their neighbors. And the model, these interactions will cease, or they'll stop once the thermal equilibrium is reached between the two spin groups. And so in the model, we've created sliders and switches that allow for variation. And so we have two types of sliders in the model. One is the percent excited slider. We have one for each spin group, and that lets us control the amount of excited nuclei in that spin group. The delta E slider basically is the difference in energy from ground state to the excited state, and that can be changed as well. There are two switches in the model. One of the switches is the world division switch, and that allows one spin group to be larger than the other. The second switch that we created was a dense setup switch, which isolates the excited nuclei to the sides of the world before they can interact.
So here's a quick layout of the interface that we created within the model. And now that we laid down the foundation, I'm going to give a quick tour of how we put it all together and organized it. So below the start and stop button, as well as the setup or the reset button, are the monitors that we used to analyze the different thermodynamic properties. So we have temp 3A and temp 3B. These are the temperatures corresponding to the spin groups. So temp 3A corresponds to the blue spin group A, and temp 3B corresponds to the pink spin group B. And below that, we also calculated for entropy and energy as well, corresponding to the different spin group A and B. And to the right of those are the corresponding plots to these monitors. So in this model, it updated every tick, which is the time value for the model. So these plots would output every tick, and that corresponded with the monitor. So you could see the rise and fall of those values while the simulation was running until it stopped once the two spin groups reached equilibrium. Now, below the monitors in green are the three sliders. We have percent excited A and percent excited B, which corresponds to the temperature of both spin groups. So in this case scenario, percent excited A is above 50%, and that results in a negative temperature, which is up at the top for temp 3A. And percent excited B results in a positive temperature for temp 3B up at the top monitor. Now, the delta EA slider is basically the energy difference between the two spin states. And below that are the switches again. They could be turned on or off to result in different scenarios and format a different change in the world on the far right.
Okay, so the switches are used to create different scenarios for the model. And so these are the 4 different scenarios that we've coded for. In the first image here on the left, this is when both of the switches are off. The world is just normal. It's split directly in half so that we can have spin group A and spin group B. And the nuclei are evenly distributed over the entire world, but the world is split in half to create the 2 spin groups. In the next image, we have dense setup switch is on, but world division is off. So the excited nuclei are isolated to the sides of the world before they interact. In the next image, world division is on, but dense setup is off. So in world division, spin group A, the blue group, is bigger than spin group B. And in the last image, both dense setup and world division are on. So spin group A is still bigger than spin group B, and the excited nuclei are isolated to the sides of the world before they interact.
So here's a quick snapshot of a successful equilibrium scenario. And the plot on the bottom shows the 2 spin systems reaching equilibrium, and the color corresponds to the spin group. So A is representative of blue, and B is representative of pink. And this fluctuation happening here with spin group B in pink is absolute negative temperature. So the model is basically jumping from positive to negative infinity until it could find that common final temperature. And this program reads values either extremely positive or extremely negative, so that's why you see that fluctuation happening there, contrary to the Kelvin scale where negative infinity and positive infinity are near each other.
So this is just a portion or a part of the code that we wrote. This section is coding for our world division switch when it's on and when dense setup is off. So at the top, where it says if world division equals true, that means that it's on, so true is for on. And where dense setup, if dense setup equals false, then it's off. So NetLogo, the program that we use to create this model, it has its own coding language. So we had to learn this coding language and apply it to the model to make it come to life. And so that's what we did here. And so when the world division switches on and we have spin group A being larger than spin group B, we had to tell the model that most of the nuclei had to go to spin group A, the larger spin group. So at the top of the code, the percent excited for world division when it's on, 75% of all the nuclei are going to go into spin group A, making it the larger one, and only 25% is going to go into spin group B, the smaller one. So this is just coding for one of those 4 scenarios. So all those other 4 scenarios have its own code along with other pieces of code in the model. So for our project, temperature is defined by this equation. 1 over temperature equals the change in entropy over the change in energy, where temperature is related to the change in energy. And so our temperature scale here is actually going from positive 0 to positive infinity, and then it makes a jump to negative infinity and runs to negative 0, where negative 0 is the hottest temperature. Okay. So to help understand the relationship between entropy and temperature, multiplicity has to be introduced. So multiplicity of a set of combined events is the number of different ways in which the set of events could possibly occur, or the number of ways you can arrange these events. So we have 2 simple examples to start off with using coins. in this example here on the left, there's 2 coins. In the first set of events, if neither of the coins were to land on tails and both of the coins were to land on heads, there's only one possible way to arrange those coins, both of them on heads. That means the multiplicity is 1. If one of the 2 coins were to land on tails, that would mean that either the first coin could land on tails or the second coin could land on tails, because there's 2 different ways to arrange that. That has a multiplicity of 2. In the last set of events, if both coins were to land on tails, there's only one way to arrange that, similar to both of them landing on heads. And because there's only one way to arrange that, it goes back down to multiplicity of 1. In the next example, now we have 4 coins. And so if no coins were to land on tails and all 4 coins were to land on heads, there's only one way to arrange that, all the coins landing on heads, which means it has a multiplicity of 1. In the next set of events, if at least one of the coins were to land on tails, that would mean that there's 4 different ways that it could happen. The first coin could land on tails, or the second, or the third, or the fourth coin could land on tails. Because there's 4 different ways to arrange that, it has a multiplicity of 4. If 2 of the coins were to land on tails, there's 6 different ways that that could happen. Either the first 2 coins, the last 2 coins, the middle 2 coins, the first and the last coin, the first and the third coin, or the second and the fourth coin. Because there's 6 different ways to arrange that, it has a multiplicity of 6. And this multiplicity is the maximum multiplicity. And it peaks here. Here is where half of the coins are landing on tails and the other half is landing on heads, and is also the most probable. In the next set of events, if 3 of the 4 coins were to land on tails, it's similar to if 1 coin was landing on tails, because when 1 coin is landing on tails, that means 3 had to land on heads. So if 3 are landing on tails, 1 coin does have to land on heads, and so it could either be the first, second, third, or fourth coin. Because of that, because of the 4 ways that it can be arranged, it has a multiplicity of 4. So now the multiplicity has decreased. The number of ways we can arrange these coins has decreased. If all coins were to land on tails, similar to if all of them were to land on heads, there's only one way to arrange that, all of the coins landing on tails. Because there's only one way to do that, it has a multiplicity of 1. So here, this trend is that there's an increase in multiplicity with an increase in number of the coins landing on tails. But it peaks at a multiplicity of 6. After that, even though the number of coins landing on tails is increasing as we go from 2 to 3, then 3 to 4, the multiplicity begins to decrease. Because the number of ways you can arrange this, its multiplicity is decreasing. And so this is applied to negative absolute temperature. So here we start at +0, a cooler temperature, and that's where the nuclei are at the ground state. And when we increase in temperature, we also have an increase in entropy. In chemistry, we learned that entropy is a measure of disorder. In a binary spin system, entropy is related to the multiplicity of the nuclei, or how the nuclei can be arranged. So we're increasing in temperature. It starts at +0. The temperature and energy are increasing, so is entropy. However, we get to the top, and it peaks. The entropy peaks. At the top is where half of the nuclei are excited, and the other half are at the ground state. And it's also reached its maximum multiplicity, or the maximum ways that these nuclei can be arranged. After this peak, the entropy begins to decrease, even though the temperature and the energy are still increasing. So we're increasing as we reach -0, which is the hottest temperature. Now the entropy is decreasing because the multiplicity and the arrangement of these nuclei are also decreasing.
So these are a couple of thermodynamic equations that we used in our model. The first equation is the definition of temperature that is normally used, but the second equation below is what we used in our binary spin system to calculate the temperature of the 2 spin systems. So this is where temperature is the energy difference between the spin states over the natural logarithm of the excited spins divided by the ground state spins. So this snippet of code here is what we used in our model to calculate the temperature. The toReport command right here allows the value of the temperature to be viewed in the monitor on the interface. And this is essentially the second equation translated into the proper NetLogo coding language. The if-else statement above that basically tells the program the correct number of patches to count for whether it be in ground state or excited state. Here are 3 graphs plotted in Inspire, another program that we learned how to use. It can analyze up to 3,000 data points. So the first plot here, total energy A versus temp 3A, or the final temperature of spin group A in this case. The points begin at +0, dip down to positive infinity, swings up to negative infinity, and then continues on to -0. Now there's a similar trend in the next graph for entropy A versus temp 3A, where it goes from +0 to positive infinity to negative infinity and then to -0. The point in the middle of the plots is the infinity range that was programmed to 0 in our code to account for the positive and negative infinities. The bottom plot, entropy A versus percent excited A, or the temperature, was recreated with our data collected from the model, which shows a similar trend to a previous slide for entropy.
So in these graphs, the percent excited for spin group A was set at different values. The top left is 51, over 61, 71, 81, and 91. And we graphed and observed the total energy in spin group B over time, which is what ticks represent in our model. And so for the first graph at the top, when percent excited of spin group A was set at 51, we have a decrease in a decrease in energy in spin group B, meaning that it's losing energy to spin group A. In the next 3 graphs, when percent excited A was at 71, 81, and 91, there's an increase in energy in spin group B, which means that it was gaining energy from spin group A. In the top right graph, when percent excited of A was set at 61, the energy in B started to decrease, but then it also increased again, and it increased to where it had started. So we concluded that most likely the two spin groups started at around the same temperature. The temperature just kind of oscillated before they reached thermal equilibrium. And so that's why there's a little bit of a dip, and then it comes back up to where it initially started.
Okay, so these are more RStudio plots that we used, and we couldn't use the Inspire plots anymore because we had more than 3,000 data points, so we had to use RStudio to collect this data. So these sets of plots are for entropy A, entropy B, and the total entropy, all versus ticks, which is again the time for the model. And in the first plot is total entropy versus ticks, which is an overall increase, which is to be expected, while entropy A is decreasing in entropy because entropy A is feeding into entropy B, which is increasing, which results in an overall increase in entropy. This is an example of an equilibrium scenario for temp 3A versus temp 3B, all versus ticks, and eventually the final temperatures of the spin systems are reaching equilibrium. Also, in this particular scenario, it was plotted with percent excited all above 50, so that's why there's a negative value on the y-axis. The bottom points in dark blue represent the cooler temperatures, while the light blue are the hotter temperatures because these are closest to -0 up at the top. So through trial and error and repeated data collecting, we successfully made a working binary spin system model, and our model can be found on the NetLogo Modeling's Commons page under binary spin lattice. We were going to show a simulation, but it just didn't work out. So you could go ahead and try it for yourself on their website. And we're expected to be published to physics teacher, and we're currently working on a virtual lab to be used in the classroom to explore negative absolute temperatures further. And we can continue on with this model and make a 3-level system, which can be used to understand how lasers work. And Jennifer and I, along with Dr. Browning, we went to the Florida Undergraduate Research Conference up in Melbourne and also presented our research there. We could take any questions at this time. Yes.
What was the most challenging part of your research?
Oh gosh. Okay. Probably, so once we got the code all set up and our model was working, we introduced the switches. So we had that world division switch, remember, where it was the smaller spin group and then the larger spin group A. So it took a long time coding for that because we had to somehow divide the spin group A into 8 different sections. So we had like a bunch of code for that so that it filled so while both switches were on and the excited nuclei were localized around, it would fill each one so it wouldn't just all be like a big blob. So that was probably the hardest one, and that took us the longest time to try to figure out. Yes?
Why did you choose to do this particular research study?
So this was for the summer undergraduate research program, and we basically needed to link up with a professor to do research, and we were both really interested in doing research over the summer, and Dr. Browning was an option, and it appealed to us. We never really learned how to code, but he reassured us. He was like, we have books, and you can learn how to do it, so we studied that, and that's how we got into this.
Yeah, so when we talked to Dr. Browning, he said he was researching absolute negative temperatures. We had never heard of that before, and it's not really a common thing that we even come across. And so to think that a temperature scale could go into infinity and -0, and that being the hottest, it was just a really cool concept for both of us. And of course, coding was a whole nother thing to it, but definitely being able to study not only coding and modeling, but being able to observe absolute negative temperature being at work in the model was really great. And so that's why we also chose to do this. Yeah. Thank you.
Any more questions?